So our next speaker is Hipolito Treffinger from the University of Bonn, and the title of his talk is on higher torsion classes.
Thank you very much for giving me the opportunity to organize this, to give this talk. And I will speak about higher torsion classes, which part of this talk is mentions work that appeared on the archive this week, which is in joint work with Jabada Sodolahi from the University of Isfahan, Sibylle Scholl from the University of Leicester, and Peter Jørgensen from the University of Aarhus. As we know, cluster tilting subcategories arise actually as a way to categorify cluster algebras that originate by Fomin and Selevinsky. But actually, the definition of cluster tilting subcategories is also valid, and it can be done in the same way, not only for cluster categories, but also for triangulated categories and abelian categories. And in fact, the definition is here. We saw it just before in Laertes' talk. Is a subcategory given an abelian category is a subcategory which, given any two objects, there are no extensions, ith extensions with I between 1 and n-1, and this subcategory should be maximal with respect to this property. And what Iyama realized is that within this these n-cluster tilting subcategories, one can do homological algebra. So many classical objects of homological algebra were generalized from the classical setting into the higher setting, the higher homological algebra. For instance, the notion of n-abelian categories as a generalization of abelian categories was introduced by Jasso. I will not go into the axiomatics of n-abelian categories, but he showed that each n-cluster tilting subcategory of an abelian category A is always an n-abelian category. And actually, last year in May, in two works independently by Kvamme and Ebrahimi and Nasr-Isfahani, they have shown that actually all n-abelian categories are of this form. All n-abelian categories are the n-cluster tilting subcategory of a suitable abelian category, right? And if one wants to do homological algebra in general, one would like to have torsion classes. The definition of torsion class, this is not the most traditional definition, but let me explain a bit. A torsion class is a subcategory of an abelian category, such that for every object in the abelian category, there is a torsion subobject. So with this an object in this subcategory T, and such that essentially there is this exact sequence in the Holmes. So essentially, this in the most classical definition of torsion classes, this sequence can be translated into the fact that there are no maps from the torsion class into the torsion-free class, right? So, so then using this phrasing of torsion classes, Peter Jørgensen defined the notion of an n-torsion class as a subcategory U of an n-abelian category M, such that for every object X, so here it should be X, sorry, for every object X in my n-abelian category, we have a torsion subobject. And then, so we have this inclusion, and then we have an n co-kernel here, and we ask that essentially there is an exactness of sequences here for this n co-kernel with respect to the Holmes coming from the n-torsion class, which comes to generalize exactly this exact sequence which we have there. However, one thing that happens in this context of n-torsion classes is that with this definition, there are no such notion as an n-torsion pair, because we have this asymmetry. So we have one object, one subobject, and then we have an n co-kernel. So it's way too long to be able to get a torsion-free class associated to this n-torsion class, right? So we are now in this situation. So we have an n-cluster tilting, an n-torsion class inside an n-cluster tilting subcategory inside an abelian category. So the question is the following: can we characterize the minimal torsion class containing this n cluster tilting subcategory? And the answer, thankfully, is yes. And this is one of the main theorems of this work with Java, Peter, and Sibille. And it tells you that an torsion class in an abelian category is the minimal torsion class containing an n-torsion class if and only if these three conditions holds. The first thing is that for every object in my n cluster tilting subcategory, the torsion object should be also in the n cluster tilting subcategory. That the torsion class is the minimal torsion class containing exactly all the torsion objects, right? And there is this third condition that there are no n-1 extensions between the torsion object of anyone in M, in the n cluster tilting subcategory, and the torsion-free object associated for this pair, which for a sanity check, when n is equal to 1, this gets Holmes. This gives us Holmes and says there are no maps between the torsion class and the torsion-free class, right? But moreover, in this case, what we have is that the n-torsion class is not other than the n-cluster tilting subcategory intersect with the torsion class that we have. So it's a really nice description of every n-torsion class. And this work has been done even if it appeared not so long ago. I mean, 3 days ago in the archive. It has been essentially done for a long time. And in September, I came to Bonn and I had the possibility to meet and collaborate socially distancing with these nice people, Jenny August, Sandra Kvamme, Karin Jacobsen, Johanna Holland, and Jan Palou. And we were a part of a group which was called tau tilting theory and higher homological algebra. So we said, okay, we have that any n-torsion class is the intersection of a torsion class with an n-cluster tilting subcategory. So the question that we asked, and was the starting point of our collaboration, is what happens when our torsion class is functorially finite? Because we are interested in tau tilting theory and we are interested in higher homological algebra. Can we say something about this? Well, the answer is yes, we can say stuff. And actually, we were able to give more properties in a paper that is being written at this moment of n-torsion classes. For instance, any torsion class is well known that is closed under quotients and extensions up to isomorphism, right? And even if we ask ourselves what happens if T was functorially finite, we were able to generalize some results, and we were able to show that if we have an n-torsion class, then it's closed under n quotients and n extensions up to homotopy. What I mean by n quotients, essentially what I mean is that if we have a map going from X to Y, where Y belongs to my n-torsion class, then the n co-kernel, so there is an n co-kernel such that every object in this n co-kernel belongs to the n-torsion class. Okay, and the same is what I mean by the n extension. So we have given an n extension, we have a representative of this n extension, we have an n exact sequence such that every object in the middle of this should belong to you as well, right? So this gives us a really nice characterization. But as I just mentioned, we were interested in Auslander-Wright in tau tilting theory, right? And tau tilting theory, for tau tilting theory, we suppose that the abelian category is the module category of some algebra. And in this case, we have an Auslander-Wright translation that we often call tau. And tau tilting theory is based, most of it, it started with the following theorem by Auslander and Smalo that says if I have a torsion pair TF, right, and I have an object T in my torsion class, so this T is X projective, which means exactly this condition, if and only if the Auslander-Wright translation of T belongs to the torsion-free part, right? In particular, this implies that this object T that we took is tau rigid, okay? And actually, we were able to generalize this because, as was mentioned just before, Iyama introduced the notion of higher Auslander-Wright translation, tau n, and using this higher standardized translation, one of the results that we got in this collaboration is that if you take an n-torsion class and an object in an n-torsion class, then this object is xn rigid, is xn projective, so there are no maps coming, no extensions in this way for every other u prime in U, if and only if there are no maps from any object in U into the tau n Auslander-Rayton translation of U. In particular, we showed that every xn projective is tau n rigid. And starting from that point, actually, we were able to show several things about the tau n tilting theory, if you wish. But this is all that I have to say for today. And if you want to hear more about this, please come to FD seminar in the 18th of February, in which I will be giving more details and more results in this about these works. Thank you very much.